Fluids are everywhere, from water and air to systems like hydraulics and buoyancy. But what's actually going on underneath all of that? In this video, I'm going to go through the core ideas of fluid mechanics, what fluids are, how they transmit pressure, why objects float, and how fluids move. The goal isn't to go super in depth, but to build a clear picture of how all these ideas connect. So what actually is a fluid? A fluid is any substance that can continuously deform. In other words, it flows when a force is applied. That includes both liquids and gases. In both cases, the key idea is that they don't resist motion. They move and reshape instead. At this level, we treat fluids as ideal, meaning they're incompressible and flow smoothly without resistance. So instead of focusing on individual forces like we do in solid mechanics, we need a different way to describe how forces act in a fluid. And that brings us to pressure. So how do fluids actually transmit forces? That's where pressure comes in. Pressure is defined as force distributed over an area. So instead of thinking about a single force, we think about how that force spreads through a fluid. One key idea is that pressure acts in all directions. That means if you apply pressure at one point, its effect spreads throughout the fluid. This leads to Pascal's principle. Pressure applied to a confined fluid is transmitted equally everywhere. That's why systems like hydraulics work. You can apply a small force over a small area and get a much larger force over a bigger area. Another important idea is that pressure depends on depth. As you go deeper in a fluid, pressure increases because there's more fluid above pushing down. This relationship is captured by this equation. Pressure increases with density, gravity, and depth. And that increase in pressure with depth leads directly to another important effect: buoyancy. Buoyancy is the upward force a fluid exerts on an object. But where does that force actually come from? It comes from pressure differences. See, since pressure increases with depth, the bottom of an object experiences more pressure than the top. That difference creates a net upward force. This is described by Archimedes' principle. The buoyant force equals the weight of the fluid displaced by the object. So instead of thinking about all the forces acting on the surface, we can just say the fluid pushes up with a force equal to the weight of what it displaces. This also explains why objects float or sink. If an object's average density is less than the fluid, the buoyant force is enough to support it and it floats. If it's greater, it sinks. So again, what started as pressure differences turns into a macroscopic force. And now that we understand how fluids exert forces, we can look at how they actually move. This is where fluid dynamics comes in. In an ideal fluid, flow follows smooth paths called streamlines. Along these paths, the motion is continuous and predictable. One key idea is that the amount of fluid flowing through a system has to stay constant. This is captured by the volume flow rate, the amount of fluid passing through a cross-sectional area per unit time. So if the area gets smaller, the fluid has to speed up to keep that flow rate constant. That's described by the continuity equation. V1A1 equals V2A2. Finally, all of this connects through energy conservation. Bernoulli's equation tells us that along a streamline, pressure energy, kinetic energy, and gravitational potential energy are all related. So as a fluid speeds up, its pressure decreases and changes in height also affect the energy balance. This gives us a complete picture. Fluids move in a way that conserves mass and energy. To make this more concrete, I built a simple program that models a fluid flowing through something like a syringe or a pipe that narrows. The goal is to see how changing the area affects the fluid's speed, the pressure, and the force required to keep it moving. So it takes in the initial area, the smaller outlet area, the starting velocity, and the fluid density. And from that, it calculates the new velocity, the pressure difference, and the force needed. So with these values, we get this velocity, this pressure change, and this required force. Now watch what happens when the outlet gets smaller. The velocity increases, but more importantly, the required force increases a lot. That's exactly what the physics predicts. When a fluid speeds up, pressure drops, so you need more force to keep it moving. So overall, fluids aren't just substances that flow. They're systems that transmit forces through pressure, convert that into motion, and follow energy conservation. And as we saw, even small changes in geometry can create surprisingly large effects. These same ideas show up everywhere, from hydraulics to airflow, which is why fluid mechanics is so powerful. And here are all my image credits. Thank you guys for watching. If you enjoyed, please consider subscribing, and I'll see you in the next one.